I hope you were impressed with my magic trick.
What's going on? Right? What's going on are some electrical forces, right? Right now, this little piece of trash, this little piece of plastic bag, is stuck to my chalkboard. Why? Electrical forces. I can do this magic trick with my magic wand. Right? Ooh, let's see. I'm losing my charge a little bit. I can make it float. So the piece of PVC pipe exerts a force on the plastic bag, even though they're not touching each other. That's really weird, right? If I want to exert a force on something, I have to touch it, right? I can't will the ball to move. There, I just tried. You weren't very impressed. I can't will the ball to move. I only exert contact forces. Electrical forces are long-range forces. Now, we've seen another long-range force last semester, and that was gravity. Of course, we've got a lot of experience with gravity, but if you really think about it, it's kind of weird, right? Like, I let go of the ball, it instantly starts falling, right? It's not like a little message has to get carried from the ball to the earth to say, hey Earth, Foxley just let go of me, you can yank on me now. Okay, bring her on down. Right. No, it's like instantaneous. Instantly, the ball starts falling. How does the ball know that the earth is there, or the earth know that the ball is there? Well, we didn't introduce this idea last semester, though we certainly could have. We could say that the earth creates a gravitational field, and that gravitational field permeates space all around the earth, including this location right here. And if nothing's there, then no object is there. Then the gravitational field exists, and that's the end of the story. However, if I put an object there, then this object interacts with that gravitational field. And the object experiences a force, a gravitational force. We can think of this experiment that I was just showing the same way. Right? The PVC pipe, once I've rubbed it to give it a nice big charge, it permeates the space all around it with something called a electric field. Let's call it an electric field. It's something that permeates space all around it. And then the plastic bag, the piece of trash, interacts with that electric field. So it's this way of sort of resolving the issue of, and the word for it is action at a distance. How does the plastic bag know that the wand is there? That's the real question. And in the previous lecture, we presented Coulomb's law. And in the Coulomb's law model, we say charge number 1 directly affects charge number 2. We don't really even get into the details of how that happens. We're just okay with this idea of action at a distance. However, what we can do is we can replace that with the idea of an electric field, where the electric field is something that permeates the space around a charged object, leading to interesting electrical results. So let's jump over to the PowerPoint here. Here we see 2 electrodes, and these are bits of iron suspended in oil, and you actually can get a sense of the electric field between these two. This is 2 charged pieces of metal, and it really is creating an electric field which permeates the space around them. So again, in the Coulomb's law model, we say that the 2 charges just affect each other, and we don't worry about that mechanism. In the electric field model, then we say, hey, well, we know there's a force between A and B. In order to get rid of this action at a distance idea, we say A creates an electric field which permeates the space all around it, and B interacts with that electric field. Now, in this case, we're using these squiggly lines to sort of say, there's something out there. As the slide says, that's a poetic license there, right? We're gonna describe a better way of drawing electric fields here in a little bit. So what we can think of then is the electric field is like, okay, I've got a charge here, and I know the charge experiences a force. So if I was to divide out the magnitude of that charge, what would be left? The electric field at that location. So the electric field is very analogous to the gravitational field, right? The gravitational field exists at this point right here. whether I put a mass there to experience it or not. The electric field created by my magic wand exists right here, whether or not I put that piece of trash there to experience it. So we're going to learn another equation for the electric field here in a little bit. But for right now, we can just say, hey, we take the force exerted on an object, say B, on a charge, say B, and we divide out the charge of it, and what's left is the electric field at that point. You can think of the electric field, it's almost like the wind. I could look out my window, and if I wasn't in the basement, I could look out my window, and how could I tell if the wind was blowing? Well, if all I've got is a view of blue sky, then I can't actually tell whether the wind is blowing or not. I can only tell whether the wind is blowing looking out my window by seeing its effect. And that's sort of analogous to what we're doing here. We're saying, well, how can you tell if an electric field is present? Well, put a charged particle there. If it experiences a force, bam, you definitely had an electric field at that point. Same thing, I look out my window. How can I tell if there's a wind? You can only see the effect of the wind. You cannot see the wind itself. That's my point. The effect of the electric field is a force. We can use that force to determine the electric field at that location. So that's the idea of the electric field. Again, the phenomenon we're talking about in this whole chapter is just electric forces or electric charges experience forces. That's what we're talking about in this whole chapter. And we're just kind of running through a couple of different ways to wrap our brains around it. In fact, the entire next chapter will be us just trying to wrap our brain around this interaction still. So again, to kind of delve into this just a little bit more, here we've got a point charge, and we've got a point charge right here, and we're interested in knowing what is the electric field right here. Well, just looking at this point right here with nothing there, I can't tell. What do I have to do? I have to place a charge at that point and observe the effect. Oh, I see that a charge placed here experiences a force. There must have been an electric field at that point. Again, we're determining whether there's an electric field there or not by observing the effect of the electric field. And notice the equation we will use here. It's exactly the same as what I showed in the previous slide. We simply divide out the charge that I placed there, and we're left with the electric field. Now I can give you an equation for the electric field due to a point charge. And it looks like this. Notice again, much like we did with the Coulomb's law and forces, we've separated out the magnitude from the direction. We'll calculate the magnitude here. R squared will always be a positive number. K is a constant. It's just 8.99 times 10 to the 9th Newtons per meters squared per coulomb squared. That's what K is. Okay, just a number. Just a number. Q, we're never going to put a negative number in here. We're always going to take the absolute value, which then allows us to get a positive number here for the magnitude, and we use our brains to figure out what the direction is. Okay, I have a couple of examples. Okay. We'll do an example here in just a second, but first let's look at how we might represent these field lines better. So we had those little squiggles. Now we're going to show a better way to represent electric fields on our piece of paper. These field lines always start on positive charges, and they always end on negative charges. Electric fields are created by charges. They affect charges also. But electric fields are created by charges. And when we're sketching electric field lines, we always start on positives, we end on negatives, and the field vector is always tangent to the field lines. What do I mean by that? The electric field is a vector. It has a magnitude and a direction, which means that at any one point in space, it can only have one magnitude and one direction. So if I've got an electric field line like this, well, that might help me visualize the electric field in this whole region. But at any one point, the electric field can only point in one direction. And notice this electric field has several different directions, a multitude of directions as you go from left to right along this path. And so the electric field at any point will always just be tangent to that curve. Again, at a specific point in space, the electric field will have a specific magnitude and a specific direction. A specific magnitude indicated by the length of my arrow, a specific direction indicated by the direction it points in. So I can look at a picture like this one right here, and the field lines give me a sense of what the electric field looks like at all points, but I need to look at the tangent to those field lines to see what the direction of the field vector is at that specific point. A couple of examples here of common electric field situations. Here is a positive charge. The electric field lines always point straight away from a positive charge. The field is always stronger where the lines are closer together and weaker where they are farther apart. Notice that this is another representation of this equation. Right? This equation tells us the same thing. What happens to the electric field? Well, it falls off as 1 over the distance squared. So it means if I get twice as far away, the electric field is 1/4 as strong. So the field gets weaker as I get away from the charge, and it points away from a positive charge and towards a negative charge. That's exactly what's illustrated here. The spacing of these electric field lines is proportional to the strength or the magnitude of that electric field. As I get farther from this dot, those lines get farther apart. Here we have what we call a uniform electric field. Here we see the electric field is the same at all points across here. How can we tell? Because the electric field line spacing is the same. Recall that the spacing is proportional to the magnitude of the field. So if the spacing is constant, the field is also constant. This is the type of field that gets created in what's called a capacitor. And we'll talk just a little bit more about that at the end of the chapter, but we'll talk quite a bit about them as we move through the semester. A capacitor is simply a device for storing charge and creating uniform electric fields. Okay, let's look at a quick example. Here we see positive charges create an electric field in the space around them, in which case is the field at the black dot the smallest. And so see here that we're changing both the charge and we're changing the radius. Now, the electric field is proportional to the charge and inversely proportional to the square of the radius. So let's just write down what these will each be, and then we'll rank them when we're done. So for situation A, well, we have that the electric field is simply kq over r squared. Okay, well, that's fairly straightforward. How about situation B? In situation B, we have that the electric field is k times 2q over 2r squared. And what do we get there if we kind of simplify this down? Well, we get 2 squared is 4 on the bottom, a 2 on the top. We have 1/2 kq over r squared for situation B. How about for situation C? For situation C, we have k times 2q over r squared. Simplifying that, we end up with 2kq over r squared. And situation D, we have kq over 2r quantity squared. We end up with we end up with kq over 4r squared. Okay, so now let's look at these. Which one of these is the smallest? Well, kq over r squared, 1/2 kq over r squared, 2kq over r squared, or kq over r over 4r squared. Definitely D is the smallest, and PowerPoint agrees. Yeah! Let's do a quick numerical example. A 1 nanocoulomb charge is at x equals 1 meter. A negative 2 nanocoulomb charge is at y equals negative 1 meter. What is the magnitude and direction of the electric field at the origin? As with any physics problem, drawing a picture is probably a pretty good place to start. Let's do that, and then we'll proceed with some numbers. Okay, so now I've drawn my charges. We're interested in the electric field at the origin. Notice there's no charge at the origin. That's fine. There doesn't have to be. The electric field can exist at the origin whether or not there is a charge there to experience it. So let's look at this. We've got the electric field from the 1 nanocoulomb charge. We know that electric fields point away from positive charges. So at the origin, away would be in this direction. Our electric field is going to look something like that. And if we call this charge number 1, then we have E1 here. We know that E2 will point towards a negative charge. If this is charge 2, it will point towards a negative charge. Notice that it will be twice as big. Why will it be twice as big? Because it has the same magnitude of charge, and it is, why is it twice as big? Because it has twice the charge, and it's the same distance away. I could use the tip-to-tail technique of adding vectors. I will move E2 over here. And the resultant, what we are looking for, points something like that. Now we know we're going to use our equation for the electric field. The electric field, in this case, we're going to use the magnitude is going to be given by KQ over R squared. So let's just figure out what the magnitudes are for these two. First of all, E1. Well, that's going to be, I'm going to round K to 9 times 10 to the 9th. That's our constant. We just look that up. And our Q for E1 is 1 nanocoulomb. 1 times 10 to the negative 9th coulombs, all over R squared. Again, that's the separation, which in this case, the problem statement says 1 meter. And we get a number. E1 equals 9 newtons per coulomb. Okay, now we're not quite done. That's just E1. We still need to figure out E2. E2 is going to be 9 times 10 to the 9th. That's our K value again. And we're going to use absolute value, right? We're not going to plug in a negative number. Plug in a positive number. 2 times 10 to the negative 9th. All over R squared. Again, still 1 meter squared. And we run our calculator, and we get E2 equals 18 newtons per coulomb. Again, these are just magnitudes. Now, what we need to do then is we need to put them together. Notice that they form a right triangle. And we want to find E total. So what we're going to do is we're going to say Pythagorean theorem. E total is going to be E1 squared plus E2 squared. Square root of that is. Like that. And so we end up getting E total equals the square root of 9 newtons per coulomb squared plus 18 newtons per coulomb squared. And we get the exciting answer that I have to... Okay, so we ran our calculator and we got an E total of 20 newtons per coulomb. not too bad. But we're not quite done because we still need to find the angle theta. And it looks like maybe I can squeeze that in right down here. Let's try and do that. So we're going to use theta. Notice we've got a right triangle. I know the opposite and the adjacent. So I'm going to use the inverse tangent of opposite over adjacent to get my angle theta. So that's going to be tangent inverse of opposite, 18 over 9, and we run our calculator, and we get 63 degrees. Okay, so again, electric field is a vector, which means our answer should have a magnitude and a direction. We found the electric field due to our first charge. We found the electric field due to our second charge. Then we added them like vectors. This process will work on every one of these electric field problems. Now, I could give you geometry that was a little trickier. I could give you geometry that was a little more straightforward. But you're going to follow the same process. The vector addition, the finding of the separate things, the vector addition, and then the finding the result.